Hi everyone, this is a video on the TP4056 power management IC. Something that I made after I purchased a few cheap ones on eBay, and I found they're a bit problematic for the following reasons. So this is typically the ones you see on eBay and lots of YouTube videos on these ones. I've never seen one actually use a genuine TP4056, which is made by Top Power. So this is TC4056A, which I believe is made by AMS, but I don't know if it's a fake or not. This works. It gets really hot because it outputs 1 amp, and this small package, I think it's TSOP8, really can't dissipate the heat quick enough via the heatsink. It's very small. The PCB is used as a heatsink. If you change this resistor here, R3, tiny, you can limit the current. Even if you go to 600 milliamps, it still gets hot. It doesn't actually damage it, so it has its own thermal regulation, so it cuts or drops the current if the T-junction temperature hits 175 degrees, I think. But I think in the long term it probably damages all the nearby components, because some of these capacitors probably aren't high grade. This module also has a protection chip, the FS8205 and the DW01, to prevent undervoltages and so on. So these TC4056s, or the cloned TP4056s, aren't particularly great compared to the TP4056, and I'll explain why. They have the tolerances are higher, meaning the charge cutoff voltage could be, instead of being 4.2, it could be 4.25 volts. Whereas the one I've made, so this is a genuine Top Power. Let me see if I can get that into focus. There you go. There's a Top Power logo on there. I bought this from a LCSC. It's genuine. It's about 20p, I think, or 30p. It's got the Top Power logo on it, and this is the 4056X version. So you can get the 4056M. The X version has a higher, better tolerance and better thermal management. So the X version cuts the charge voltage at 1%, which I think is maximum 4.218 or something like that. I can't remember. Whatever 1% is, as opposed to this is 1.5% tolerance. So the reason why I made my own version, which is this one here, because I needed one with 4 or 5, 6s to charge 4 separate batteries, and I didn't need the management chips for the discharge, because I'm using a different board for that. This is purely for charging, and I needed to, well, this is an afterput, I needed to put heat sinks on, so I've also limited the charge current. So this is what the PCB is I've designed. So I'll talk about the schematic later, and the EasyEDA Project will be available. So grounding plane on top and bottom, which acts as a heatsink. Because I don't have liquid solder, and I really don't want to mess with that, and I don't want to mess with hot air guns, I made a biggish hole there, and then when I soldered on the TP4056s, I then put a blob of solder through there to weld the other side. It seems to work. Got all the LEDs here along the bottom, holding this wrong way up. I split the outputs just so I can mount it properly. So I've set the R3, which is these ones here, going across here, to 2 kilo ohms, which limits the charge current per battery to 580 milliamps. Still generates quite a bit of heat, so even if a 5 volt input. I've also then put 4 2-watt resistors at half an ohm, which drops I think 0.3 volts, and I can't remember what the wattage is, half a watt or something like that. So some heat is also dissipated by the resistor to take some of the load off. So when I first ran this module without the heat sinks, it was getting hot, 70 degrees on the whole board. So that's quite close actually to the temperature of the LEDs here. And not all the capacitors that I used are COG, so these are X7Rs 10 microfarads. It obviously affects the rating, so a board like this, which is cheap and has actually more capacitors because of these extra circuits, I don't think these circuits will probably do too well, or the tolerances will vary depending on the temperature increase, and running at 70-80 degrees isn't really good. So I decided to retrospectively get a bit of very fine sandpaper, 1200 grit, and polished off and exposed the copper. Cleaned it with this contact cleaner, and then used the following glue, which is quite cheap, 3 quid for this 5 gram. So this is a thermal glue, quite popular on eBay, so anyone you can really buy. Put these on, let it dry for 24 hours, and I'm not sure I can actually take this off without breaking something. It actually is stuck on. So I think the glue doesn't then melt unless you hit 300 degrees or something like that, or 250, I can't remember. So seems to work. I did a quick test. It seems to be dissipating the heat much better. This was uncomfortably hot when I touched it, including the resistor. Now these seem to be dissipating the heat. So I've put this together. The batteries I'm going to use in my next project. 4 batteries, all going to be wired up to charge them individually, because these are all individuals. It's a 5-volt input, by the way. And then I have this, also part of my project. It's a LDO regulator, takes 12 volts and outputs 5 volts at 3 amps. It's all been designed to give maximum efficiency. I think this runs at 86% efficiency, so it's a boost, a buck converter. It still kicks out quite a bit of heat, so this heatsink here helps with that. So I'm just going to plug this in. So which way round is it? I think this way round. 5 volts here. So this is 5 volts. The 2 in the middle are the battery and the ground. 5 volts. 2 in the middle, battery, and then ground. Let's plug this in. So this goes in here. Okay, that's in. Just double check, don't want to burn anything. So ground, 5 volts. Alright, let's turn it on. So this power input here is 12 volts, can deliver up to 4 amps. And each one of these chips will charge up to 580 milliamps, so that's nearly 2.4 amps. So let's turn it on. So when it goes red, that means it's charging, and then I can already feel it slightly warm. Let me take a few temperature measurements. It's at the moment, it's increasing, just above room temperature. This is not warm yet, so I'll let it charge up. Let's see how the batteries are doing. So I've got a multimeter here. So all these batteries are balanced at the moment. I think they were on 3.5 volts. So let's see. Move my hand out of the way. So you can see it's charging at 3.6 volts. It's constant current, constant voltage. So it looks like they're quite well balanced at the moment. Let's see what the current measurements are per battery. It's not a reliable reading. Let me try on this battery. So it's a soft start. So at the moment it's, I mean this probably is inaccurate. 300 milliamps. Let me check this battery. There you go. I think this cheap multimeter here is not brilliant. There you go. It is hitting the 580 milliamps, so 0.06 amps. So these batteries are being charged at the maximum current now. Just check this other one. Yeah. It seems like if I connect to the negative terminal, it shows me the correct. Let's check this one. There you go. Unfortunately, this doesn't go to millivolts or milliamps. So yeah, all four batteries are charging at 580 milliamps. So this should be getting warm. Yes, it's warm, but not uncomfortably hot like last time without the heat sinks. So let's take some temperature measurements. Let's get this in the right place. Let's do it for laser. I find the laser is very unreliable. There you go. Highest temperature is 43 degrees, which is much better. And the boost buck converter, barely warm. Room temperature, yeah, feels like room temperature. And let's take reading from the other side. Looks about the same, about 40-ish degrees. So I'm going to touch the individual components. So before, this was uncomfortably hot. Yeah, so this is hottish, but it's not burning my finger like it was last time. That's what this does, by the way. If you leave this on 1 amp and touch it, you'll burn your finger. The resistor in the back is dissipating heat, but not to the point where it's going over the limit. I would say it's probably about 45-ish. Just I can tell just off my finger. It's very difficult to take a measurement with this because it's such a small surface area, but the temperature is correct. So adding these heat sinks made a difference. Maybe I could redesign this and have the copper area exposed, and maybe make it a couple of mils high as well. So talk about the schematics next. Here's the schematic for the TP4056 charging module. It's made of 4 modules, so it can be built individually. At the time of me designing the schematic, I used the 4056M, which has a smaller thermal pad. I don't think it really makes too much difference. We're talking about half a mil, I think, in difference on the thermal pads. I'm not sure. The resistors for the LEDs can be changed to limit the current based on the types of LEDs you have. Because I was using super bright green, I had to use a 10k resistor, and I was using red for the charge indicator, which typically is low brightness, so I used a smaller resistor, 5.1k. Because I've omitted the DW01 and FS8205 protection ICs, it's a much simpler, it's just purely charge circuit with a safe cutoff voltage. There's some calculations here, so I've changed the R3 values, which are these ones here, to 2k, which limits the charge current to about 0.6 amps. There is a variation of plus minus 10%. Some formulas here to work it out. So the power dissipated by the resistor here and the chip itself. So first of all, the resistor power dissipation is 0.18 watts because it's dropping 0.3 volts. Value is 0.5 ohms, so 0.18 watts is always dissipated by the 2 watt resistor. And the best and worst case power dissipation by the TP4056. So let's just say the voltage has been discharged to 3.2 volts, you've got a power supply of 5 volts. So you take away 5 volts, take away 3.2, and the 0.3 from the resistor gives you a total multiplied by 0.6 amps, gives you nearly 1 watt of power dissipation, which is obviously quite high for this type of chip. It's recommended to run it with a heatsink, although all those modules you buy on eBay don't really have a heatsink on it, and then if you touch it, it is very hot. And then let's say the battery is up to 4 volts, then the power only dissipated by is only 0.42 watts. So that will be warm to the touch. And also as it comes near to the end of the charge, the current drops anyway. It's 1/10 charge cycle, constant current, constant voltage. Here's their cut voltages for the 2 different variations. So these are for the genuine top power parts. I have no idea what the cutoff voltages are for the other stuff that you get on eBay. I'm not even sure you can trust their spec sheets. So the first version of the top power, the 4056M, had a tolerance of 1.5 volts. So that gave you a potentially worst case cut voltage of 4.263. The one I've used, the TP4056X, has a 1% tolerance, so the maximum cut voltage is 4.242, which is a lot better. Well, it's below 4.25. It also can swing the other way, so it could be 4.1 something. Let's have a look at the PCB. So here's the PCB. The firmware pad is slightly smaller than compared to the 4056X. I don't think it's really made any difference. Try to keep it as small as possible, bearing in mind the power dissipation as a resistor. Because it's a 2 watt resistor, I didn't actually waste any space by allocating thermal pads for the resistor. I don't think it's necessary, and it's only dissipating 0.18 watts. It seems to be okay. I've measured it again, it's been running for a couple of hours. The temperature it's hit across the whole board is about 50 degrees, so that's fine. Let's have a look at the circuit. So it's top view, bottom side. There are the resistor pads without the additional thermal dissipation, but everything else that's connected to the TP4056 is grounded to give the maximum dissipation. And then the 3D view. Everything is surface mount 0805 size components. Thanks for watching.